All right, so in the first problem on homework 12 is to use the inner products to prove excuse me, a result from high school geometry. So in geometry, there's a theorem that says if you take a parallelogram, and let's say the length of this side is A and the length of this side is B, let's suppose I label this rather A, B, C, D. So we have the lengths of the sides. Well, I can call this A and this B, and then this is A and this is B. And I also have the two diagonals. I have this diagonal, and I have this diagonal. And let's say the length of this diagonal is C, and the length of this pink diagonal is D. And the parallelogram law says that if you sum the squares, sorry, this is A and this is A and this is B, A squared plus B squared plus another A squared plus another B squared, that's the same as the sum of the lengths of the diagonals, C squared plus D squared. So in the simplest example, for if you have a square and the side is A, you know that the diagonals have length square root of 2 times A. And this simply says that A squared plus A squared plus A squared plus A squared is 2A squared plus 2A squared, right? This is 4A squared, and this is 2 times 2A squared. So this simple fact about a square is generalized to parallelograms, and there are lots of ways to prove that. But the way I observed you should be able to prove it is by using vectors. So if you draw your parallelogram, if this is the vector u, and this is the vector v, then from here to here, this is u, this is v. This vector is u plus v. And this vector is v minus u. And what we want to prove is that the sum of the lengths of the sides, so the length of the vector is the length of u squared plus the length of v squared, right? This is the sum of the squares of the the lengths of the four sides of the parallelogram should be equal to the length of the diagonal squared plus the length of the other diagonal squared. So this vector identity, if it's true, is the parallelogram law. So let's just do the calculation. What is the length of u plus v squared plus the length of u minus v squared? So the length of a vector is the inner product of the vector with itself. This is u plus v comma u plus v plus u minus v comma u minus v. This is the length of u plus v squared, and this is the length of u minus v squared. And when you expand this using the bilinearity of the inner product, this is uu plus uv plus vu plus vv. That's the first. And when you expand this, you get uu minus uv minus vu plus vv. And the inner product of u and v and the inner product of v and u are the same because an inner product is symmetric. So here I have 2uv Here I have minus 2uv. So these cancel, and I'm left with this plus this. I have 2uu plus 2vv. That's 2 times the length of u squared plus 2 times the length of v squared. So using vectors, one gets a very simple proof of the parallelogram law. So that's just kind of interesting. And if you didn't know the parallelogram law, now you do. It's one of the basic facts in geometry. Okay. The next two problems have to do with computing the orthogonal complement of a set. So in problem 2, we take the vector space R2 with the standard inner product, and we take X to be the set consisting of just the vector 1, 1. So X perp, it's all vectors XY in R2 such that XY and 1, 1 are perpendicular to each other. That means their inner product is 0. But of course, the inner product of these two vectors is X plus Y. So this is all vectors XY in R2 such that X plus Y equals 0 or Y equals minus X. So this is all vectors of the form X minus X for any X in R, which is just all scalar multiples of the vector 1 minus 1. So X perp, this is the one-dimensional subspace. Because it's all scalar multiples of a single vector. And geometrically, of course, here's the vector 1, 1, and perpendicular to it, is the vector 1 minus 1. So we started off with this vector, and everything perpendicular to it is exactly everything on this line, all scalar multiples of 1 minus 1. In problem 2b, we have X equal to the vector 2, 3. So here's the vector 2, 3. And geometrically, what we want to find is everything perpendicular to it. So X perp is all the vectors XY in R2 such that the inner product of XY in 2, 3 is 0, which is just all XY, all vectors XY in R2 such that 2X plus 3Y is 0, which is the same as Y equals, well, Y equals minus 2/3 X. So this is the set of all vectors of the form X minus 2/3 X for any X. Or I can factor out, if I like, X over 3, all vectors of the form 3 minus 2, scalar multiples of that. Because if you let X equal 3 and Y equal minus 2, you get 0. So this is the vector 3 minus 2. And every vector that's a scalar multiple of this that is on this line, that's everything perpendicular to 2, 3. Any questions? Then, okay. In problem 3, we're looking for these orthogonal complements in R3. So here V is equal to R3. And in the first problem, A, X is just the single vector 1, 1, 1. So in XYZ space, it's sort of hard to draw this. This is this vector 1, 1, 1, and we want everything perpendicular to it. So X perp is all vectors X, Y, Z.
Professor?
Yes.
Can you bring the paper a little bit down? Yes. Thank you.
Yeah. We want all vectors X, Y, Z such that the inner product of X, Y, Z and 1, 1, 1 is 0, which is all vectors X, Y, Z. What is this inner product? X plus Y plus Z equals 0. Or if you like, this is all vectors X, Y, Z, where Z is equal to minus X minus Y. So we're looking at vectors of the form X, Y, Z, but Z is minus X minus Y. I can write this, if I like, as X0 minus X plus 0 Y minus Y for any X and Y. This is X times the vector 1, 0 minus 1, and Y times the vector 0, 1 minus 1 for any X and Y. So X perp is the set of all scalar multiples, all linear combinations of these two vectors. So this is a two-dimensional subspace because these two vectors are linearly independent. So, I mean, I can't draw this I can't draw it at all, but this is a plane through the origin perpendicular to this vector 1, 1, 1. Geometrically, in three-dimensional space, the set of points perpendicular to a single vector is a plane, two-dimensional subspace through the origin. I mean, just the easiest example, suppose I take X to be the set consisting of just the vector 0, 0, 1. So that's just a unit vector in the Z direction. And in this case, X perp would be all vectors X, Y, and Z, such that X, Y, Z inner product with 0, 0, 1. But what is that inner product? That's just Z equals 0. It's just all vectors with Z equal to 0. And that's the XY plane. So in this case, it's really easy to see what's going on. My set X consists of just this unit vector on the Z axis. And what's perpendicular to the Z axis is the XY plane. And something's in the XY plane precisely when its Z coordinate is 0. So that two-dimensional plane is the subspace perpendicular to this vector. So the geometry here is very pretty. And in general, in 3 space, the subspace perpendicular to a non-zero vector will be a plane. But in the next example, we take 2 vectors in 3 space. So here in R3, we take X to be the set consisting of the vector 1, 0, 0 and the vector 0, 1, 0. And we want everything perpendicular to these 2 vectors. Now, if you draw a picture, you can see what that is right away, because 1, 0, 0, that's just a unit vector in the x direction. And 0, 1, 0, that's a unit vector in the y direction. And what's perpendicular to these two? The z-axis. Anything on the z-axis is perpendicular to both of these vectors. And let's see how that comes out. Just doing the algebra, x perp is all vectors x, y, z such that x, y, z and 1, 0, 0 have inner product 0, and x, y, z 0, 1, 0 have inner product 0. So that's all vectors x, y, z. What does this equation say? This equation says x equals 0. And this equation says y equals 0. So it's all vectors where x and y equal to 0. That means it's all vectors 0, 0, z for any z. Or if you like, all scalar multiples of the vector 0, 0, 1. So 0, 0, 1, that's just a unit vector in the z direction, and the scalar multiples are just the z-axis. So the subspace of R3 perpendicular to these two vectors is just the z-axis. Part C is a little bit more interesting. Here I have, again, two vectors in R3. One of them is 1, 2, 0, and the other is 0, 2, 3. And we have a vector x, y, z is in the x perp, the orthogonal complement of this, if and only if the inner product of x, y, z and 1, 2, 0 is 0, and the inner product of x, y, z and 0, 2, 3 is 0. This is the equation x plus 2y equals 0, and this is the equation 2y plus 3z equals 0. So this says that x, y, z, this vector is in x perp, if and only if these equations are satisfied. X plus 2y equals 0, 2y plus 3z equals 0. If I want, I can write x in terms of y and z in terms of y. So this is x equals minus 2y, 3z is minus 2y, so z is minus 2/3 y. So if and only if x, y, z is equal to minus 2y, y, minus 2/3 y, which is y times the vector minus 2, 1, minus 2/3, or if I want to factor out a minus 3, this is like minus y over 3 times the vector (6 minus 3, 2). I think this is right. This is minus 2. This is 1. This is minus 2/3. And 6x plus 2y is 0, and 2y plus 3x is 0. So I just did this to avoid having fractions. So x perp is just all scalar multiples of the vector 6 minus 3, 2. So this is one-dimensional. And again, we can check the inner product of 6 minus 3, 2 with the vector 1, 2, 0 is 6 minus 6 plus 0 is 0, and 6 minus 3, 2, inner product with the vector 0, 2, 3 is 0 minus 6 plus 6 is 0. So I can't draw it. I mean, I don't know how I would draw, 6 this way and, 6 this way and minus 3 that way. I mean, I can't really draw it because it's very hard to draw something 3 dimensions in a 2-dimensional piece of paper. But this is the answer. The perpendicular, the orthogonal complement to the set X is a 1-dimensional space spanned by this vector 6 minus 3, 2. Any questions about this? Okay. Problem 6, this was problem 3. Problem 4 is W is a subspace of V, and we want to prove W is equal to V if and only if W perp consists of just the 0 vector. So we did prove the following theorem. When you have an inner product space V and a subspace W, well, let's see. W perp is all vectors V and V, such that the inner product of V and W is 0 for all W in the subspace. So if suppose W perp is equal to V, what does that mean? Then the inner product of V and W is 0 for all V in the vector space and W in W. Suppose W is not not 0. Then there exists a vector W in the subspace, which is different from 0. But of course, W is in V, because W is a subspace of V, which means the inner product, actually I could have just said, let me just make it easier. So suppose W perp is equal to V. Let W be any vector in W. Then W is also in V, so inner product of W and W has to be 0, because V is equal to W perp. Every vector is perpendicular to everything in W. So the inner product of W with itself is 0, but that only happens when W is equal to 0. So W only contains the 0 vector. So if you have a subspace and everything orthogonal to it is everything in the vector space V, your subspace has to be 0. And the converse is simpler. If W is 0, then the inner product of V and 0 is 0 for all V in the vector space. So W perp is equal to all the vector space. If the only vector in W is 0, everything has inner product 0 with it. So everything is in W perp. So that's the proof. And this is true for any vector space with an inner product. Problem 5 is an application of the Cauchy-Schwarz inequality, which says that in an inner product space for any vectors u and v, the absolute value of the inner product of u and v is less than the length of u times the length of v. And in Rn, with the standard inner product, if u is the vector x1 to xn, and v is the vector y1 to yn, then the inner product of u and v is summation xi, yi. I goes from 1 up to n. And the length of v, the length of u, is summation x sub I squared square root, and the length of v is summation y sub I squared, and then you take the square root. So the Cauchy-Schwarz inequality says the absolute value of summation xi, yi for any real numbers xi and yi is less than the square root of summation x sub I squared times the square root of summation y sub I squared. And if you want to get rid of the square roots, you can just square everything. So you get summation xi y sub I squared, I goes from 1 to n, is less than summation x sub I squared, I goes from 1 to n, times summation I goes from 1 to n, y sub I squared. So this is the Cauchy-Schwarz inequality that you use in calculus a lot, at least in 2 or 3 dimensions. And if you let y sub I equal, this is for any real numbers, any numbers at all. So if you let y sub I equal 1 for all I, what you get is summation x sub I times 1, which is 1, summation x sub I, y goes from 1 up to n, squared, is less than or equal to summation x sub I squared, I goes from 1 to n, times summation 1 squared, I goes from 1 to n. This is just adding 1 to itself n times. This is n times summation x sub I squared, I goes from 1 up to n. That's the proof. That's what we had to prove in problem 5. So you just take the Cauchy-Schwarz inequality for real numbers like this, and let y equal to 1 for all I, yi equal to 1, and you get the inequality that we needed to prove. Okay, that was problem 5. After 5 comes problem 6. So C01 is just the set of all continuous functions y equals f of x defined on the interval from 0 to 1. You know, all the functions you know from calculus, but any y equals f of x, that's a continuous function. And this is a vector space. This is a real vector space over the reals, because in calculus, they teach you that the sum of continuous functions is continuous. The product of continuous functions is continuous. Scalars, constant functions, are continuous. So if you take a function and multiply it by a scalar, you get another continuous function. And all of the requirements of a vector space are satisfied. And if you take functions f and g, continuous functions from 0 to 1, the product is continuous. You prove that in calculus, or they teach you that in calculus. And define f comma g to be the integral from 0 to 1 of f of x, g of x dx. And you have to show this is an inner product. So you have to show that this is a bilinear form that is symmetric and positive definite. But again, this is all just what you learned in calculus. If you take the inner product of f1 plus f2 comma g, that's the integral from 0 to 1 of f1 plus f2 times g dx, which is the integral from 0 to 1 of f1 of x, g of x dx, plus the integral from 0 to 1 f2 of x, g of x dx, which is f1 comma g plus f2 comma g. So it's additive in the first variable. And if I multiplied f1 by c, I'd have a c here and a c here, but the integral of a constant times a function, you can always take the constant outside, you would get this. So this is certainly, if you fix g, a linear map in terms of the first variable. It's also symmetric because g comma f is the integral from 0 to 1 g of x f of x dx, but g of x f of x is the same as f of x g of x. That's the inner product of f and g. So this is symmetric. And if I take the inner product of a function with itself, that's the integral from 0 to 1 of f times f of f. That's x squared of f. And the square, this is non-negative. And again, in calculus, suppose you have a function and at some point it's different from 0. Let's say the square, so it's positive. At some point a, that means there's some interval where the function is positive. This is just continuity. And the integral is going to be positive. This is greater than 0 if f of x is not the 0 function. This is, again, this is all just a little bit of elementary calculus, but this tells you that calculus comes up very naturally, in linear algebra comes up very naturally in calculus. And this integration gives you, it defines an inner product. And Cauchy-Schwarz is valid. The Cauchy-Schwarz inequality let me just write it like this, just square both sides. This is valid in every inner product space, V. So if we let V be the space of continuous functions from 0 to 1, and we let U be a function f of x and V be a function g of x, this says that the absolute value of the inner product of f and g is less than or equal to the length of f squared times the length of g squared. But what is this? The inner product of f and g, that's the integral from 0 to 1 of f of x, g of x dx squared is less than, what is the norm of f squared? It's the inner product of f with itself. That's the integral from 0 to 1 of f of x squared dx times the norm of g squared, which is the integral from 0 to 1 g of x squared dx. So from the simplest inequality in linear algebra, we get this very important estimate for the size of an integral in calculus, in analysis. The integral of f times g is less than the integral of f squared times the integral of g squared. And this is really very, very, very interesting. Now, when you have an inner product space, it's always interesting to find orthogonal sequences of vectors, vectors that are mutually perpendicular. And part of the basis of what's called Fourier series is what is shown in problem 7. We take V to be, again, this vector space of continuous functions from 0 to 1. And for n greater than or equal to 1, let the function s sub n of x be the sine of 2 pi nx. So sine x is continuous. This is certainly a continuous function. This is just when x is 0, it's 0. When x is 1, it's 0. And this is just some function oscillating between -1 and +1. And we want to prove that the sequence of functions, or the set of functions, s sub n of x, and going from 1, 2, 3, and so forth, is orthogonal. Orthogonal means Sm comma Sn, that inner product is 0 for m different from n. Right? Vectors are orthogonal, that means perpendicular, if their inner product is 0. And the inner product is the integral from 0 to 1 of Fsm of x, Sn of x dx. Or the integral from 0 to 1 of sine 2 pi mx sine of 2 pi nx. We have to show that's equal to 0 for m different from n. Well, calculus, first year calculus is a prerequisite for linear algebra, though I'm not going to ask you to do this on the final exam, but how do you integrate this? I mean, so this is certainly something that you learned in Math 176, second semester calculus. And one way to do this is to recall some trig identities. So you remember that for any angle theta, cosine of 2 theta is cosine squared theta minus sine squared theta. Or maybe what's more interesting is cosine. So this is a special case of the addition formula. Suppose I have angles alpha plus beta. This is cosine alpha cosine beta minus sine alpha sine beta. And if I have cosine of alpha minus beta, that's cosine alpha cosine of minus beta, but cosine is even. Cosine of minus beta is the same as cosine of beta. Minus the sine alpha times the sine of minus beta, but the sine of minus beta is minus the sine of beta, which makes this plus. So I have these two trig equations. And if I subtract, let's say, cosine alpha minus beta minus cosine of alpha plus beta. This minus this, these cancel. I get 2 sine alpha sine beta. So that for any angles, alpha and beta, sine alpha sine beta is a half cosine of alpha minus beta minus cosine of alpha plus beta. Now, remember, I'm interested in the integral of sine 2 pi mx sine 2 pi nx. So if I let alpha be 2 pi mx and beta be 2 pi nx, I get the following, that the sine of 2 pi mx times the sine of 2 pi nx is equal to 1/2 the cosine of alpha minus beta. When I subtract alpha minus beta, I get 2 pi m minus nx minus the cosine of alpha plus beta, which is 2 pi m plus nx. And the reason I do this is it's hard to integrate sine times sine, but it's easy to integrate just the cosine. So let's do that. The integral from 0 to 1 of sine 2 pi mx sine of 2 pi nx dx equals the integral of this. 1/2 times the integral from 0 to 1 of cosine 2 pi m minus nx dx minus the integral from 0 to 1 cosine of 2 pi m plus nx dx. And you remember from calculus, the cosine, the integral of the cosine is the sine. So this is 1/2 sine of 2 pi m minus nx. This is if m is different from n. Over 2 pi m minus n, evaluated from 0 to 1, minus the cosine of 2 pi m plus nx. So, sorry, minus the sine of 2 pi m plus nx over 2 pi m plus n. This evaluated from 0 to 1. But the sine, when x is 1, this is a multiple of 2 pi. When x is 0, it's 0. These are both 0. Equals 0. Done. I win. So if m is different from n, this integral is 0. It's actually interesting to calculate what happens if m is equal to n. The integral from 0 to 1 of sine 2 pi, if m equals n, I'm just squaring this function, 2 pi nx squared dx is equal to what? If m equals n, this is 0. Cosine of 0 is 1. I'm just integrating 1 from 0 to 1 times 1/2. That's 1/2. If m is equal to n, this is 0. I get 1/2. So this just tells me what. So this is the inner product of sine 2 of Sn with itself. So that's what I wanted to prove. This. If I take these sine functions, if m is different from n, the inner product is 0, so they're orthogonal. And if I normalize this slightly out, they would actually be orthonormal. Okay. Problem 8 is just to prove an identity about vectors in an inner product space. So U, V are vectors in V. I want to calculate something sort of curious. I take the vector U minus V, and I look at the square of its absolute value, and I take the vector U plus V over 2, and I take the square of its absolute value, multiply it by 2, and add. So let me just make one observation. Remember, for any vector W, the length of W squared is the inner product of W with itself. So for any scalar C, the length of CW squared is CW, that inner product with itself, which is C squared, the inner product of W with itself, which is C squared times the absolute value of W squared. So this is 1/2 U minus squared V plus 2. And so by what I just said, this is the vector U plus V multiplied by 1/2. This is 1/4 the length of U plus V squared. And 2 times 1/4 is 1/2. So this is 1/2 U minus V squared plus U plus V squared. Actually, the first homework problem told me what this is. This is the parallelogram law. So this is 1/2 2 times the length of U squared plus 2 times the length of V squared. So this is U squared plus V squared. Okay. Now, one reason why this is interesting is because of an ancient theorem from Greek geometry called, well, it's due to the mathematician Apollonius. Oppollonius. I'm not quite sure about that. Apollonius' theorem. So Apollonius' theorem is the following interesting, curious fact. Suppose I take a triangle, any triangle, and let's say this is A, B, and C. Those are the vertices. So let's say the length of this side is B, the length of this side is A, the length of this side is C. And then I take the midpoint of AB, and I draw the line. So this C is really just referring to the length of AB. And I'll call this point, let's say D. So D is the midpoint of AB. And I'm going to let the length of CD, call that D. So I have a triangle with sides A, B, and C, and D is the length of the line from the vertex C to the midpoint of AB. And Apollonius' theorem says that A squared plus B squared is equal to 1/2 of C squared plus 2D squared, which is a kind of a strange identity, but it has a certain similarity to the vector identity we just proved, which is the length of U squared plus the length of V squared is 1/2 the length of U minus V squared plus 2 times the length of U plus V over 2 squared. So I want to see if I can translate Apollonius's theorem into a vector form, and this would give me the proof. So if I let, for example, this vector be u, let this vector be v, let's say, and this vector be u, then this would be u plus v. This vector and this vector, and this is half of it. So this is u plus v over 2. And this vector is what I add to u, what I add to v to get u. This vector is u minus v. So looked at in this way, this is v, this is u, this is u plus v over 2, and this is u minus v. And if you can understand this picture, then without doing any work to speak of, I mean, the work is in this picture, you get the result. Maybe another way to see this would be as follows. I have a triangle, and I call this A, B, and C, and I draw this. So these lines are parallel and these lines are parallel. So now I have a parallelogram. And if I let this be V and this V and this U and this U, this vector is U minus V. And this long diagonal is U plus V. So this part is U plus V over 2. And the parallelogram law said 2 times the length of U squared plus 2 times the length of V squared is equal to the length of U plus V squared plus the length of U minus V squared. So the length of U squared plus the length of V squared is a half of this. It's a half of U plus V squared plus a half of U minus V squared. This is equal to a half is the same as 2 over 4. So this is 2 times the length of U plus V over 2 squared plus a half the length of U minus V squared. And we have the 3 sides of our triangle plus this side right here. AB is U minus V. CD is U plus V over 2, and AC and BC are V and U respectively. So if you convert the triangle, just take them to a parallelogram, you get Apollonius's theorem right away from the parallelogram law. In any case, this is just stuff to think about. You maybe even think about after the term is over, because I'm not going to have this on the final exam, but because the final exam is more straightforward problems involving the material in the course. Any questions about any of this? We have a class this afternoon and a class tomorrow morning. And the purpose of those is really just to answer questions about everything. I'll try to put together a review sheet also, which you'll have in a couple of hours, perhaps. I'll try to have it before the afternoon class. Any questions?
No, thank you. I was actually going to ask about that, or like the study methods. So thank you.
I'm sorry, is there still a question?
No. I said you, like what you just said answered the question I was going to ask.
Okay.
Yeah.